The topic of this lecture is hypothesis testing, and for clarification, we're not going to go through all of hypothesis testing. We're just going to get into an introduction of it because there are several different applications when we can learn a little bit more about hypothesis testing work. So for now, we're just going to start with the basics of it, where we're looking at the objective being trying to evaluate a statement that we make about a population. And so hypothesis testing is going to be a procedure where you look at the evidence and you use probability theory to make a determination about whether or not your hypothesis is a reasonable statement. And we're going to talk about it in terms of a 6-step approach. So the first step is to state your null hypothesis and your alternate hypothesis. So sometimes null hypothesis is denoted with H sub 0. Sometimes it's H sub O. Your alternate hypothesis is sometimes H sub 1. Sometimes it's H sub A. So you might see HOH1. Sometimes you might see HOHA. They mean the same thing. But basically your null hypothesis, null means 0, nothing, the same. Okay? So your null hypothesis is that you're going to maintain the status quo. Okay, so when you're looking at the statement for a null hypothesis, it's going to have an equal sign in there somewhere. So it's either going to be, for example, my sample mean is equal to my population mean, or it's greater than or equal to, or less than or equal to. So that null hypothesis is the statement that you evaluate to determine if you reject it or not reject it, based on our sample data to provide convincing evidence about whether or not that statement is false. When you fail to reject that null hypothesis, it doesn't prove that your null hypothesis is true. It just means that we don't have enough evidence to prove that it is not true. So then, if you reject the null hypothesis, then you move on to your alternate hypothesis. And that would be what you would use for your conclusion. So we turn to the alternate hypothesis only if the data suggests that our null hypothesis is not true. So once you write your HO and HA, you then select your level of significance. And this is your alpha value. So you get to choose your alpha value. Typically in classes like this, you're going to use 0.05, just so that we're not always having to tell you all the time 0.05, 0.05. But also because 0.05 is very common in like consumer research. Okay, if you want to do something in terms of quality assurance, quality control, you're looking at product testing or even medical research, you might want to set a smaller alpha value of 0.01. Or if you're doing an exploratory type research, you might increase your alpha value to being 0.10. And basically what that alpha value is that area outside that an observation might fall in error, basically. And so your alpha value is associated with your type 1 type of error that we'll talk about here in a few slides. But basically that alpha level is your risk that your model has built into it of you rejecting the null hypothesis when you should not. So when I ask you about the risk of your model, I'm really asking you about your alpha value for your model. So once you've done that, now you're going to use your test statistic. And your test statistic is really going to depend on the type of information that you know. Okay, up to this point we've done a lot of work with the z-score. And so you can use a z-statistic if you know your population mean and you know your population standard deviation. And so this is what you've seen when we were looking at picture 2 from the sampling distribution of, or the mean of the sampling distributions. Okay, so we can use that test statistic to determine if my sample mean is statistically different from my population mean, for example, in the case of using the Z statistic. And then once we do that, we're going to make a rule. Okay, so if we end up with this result, we're going to reject our hypothesis, and if we end up with that result, we're going to fail to reject our null hypothesis. And that's all you're doing. You're setting that dividing line, or your critical value, that's going to say, to this side, we're going to reject, and on this side, we fail to reject. So your critical values are you've done a lot of work with this before when you were calculating the area of the curve, under the curve, using your z-scores when we were looking at distributions. So same concept here where you're looking at those values. So in step 5, you make a decision. So you select a sample, you compute the value of your test statistic, you compare the value of that statistic to whatever your critical value is, and then you determine, okay, if I'm in the shaded region or I'm not in the shaded region, you determine then whether or not you reject or fail to reject your null hypothesis. So if the results of the test result in a decision not to reject the null hypothesis, we can say that based on the sample data, the difference between the sample mean and the hypothesized population was not large enough to reject the null hypothesis. On the other hand, if the results of the test result in the decision to reject the null hypothesis, you have disproved the null hypothesis with a stated probability of that type 1 error, 0.05, right, or 0.01, whatever you set your alpha is at, right? Your alpha, once again, is that probability that you're going to make an error, okay? So there's a small probability that the decision to reject the null hypothesis was an error due to random sampling, is what you're looking at when you're looking at type 1 or your alpha. So then, after that, you know, you say, what can we say about our result based on these results? Okay, so that's where this picture comes into play. You make a decision, right? So the man asks the woman to marry him. The woman says, I failed to reject the null hypothesis. So now, based on failing to reject the null hypothesis, he needs to make a decision. And it's not really a choice at that point, because if you get either you reject or fail to reject, there is a specific decision that goes with either hypothesis. So remember, once again, when you are hypothesis testing, your results at the decision phase are to reject or fail to reject. But when you make your when you interpret your results, you may choose to accept the offer or decline the offer. Okay, so that's something that I find that students really kind of get muddled up on, because when you work on your practice problems, you might have to ask, okay, do we accept this offer? And you're not accepting or not accepting the hypothesis. That part actually comes more into play when we look at interpreting our results. So there's actually two kinds of hypothesis testing that we do. We have one-tailed and two-tailed tests. So one way to determine the location of the rejection region is to look at the direction of our inequality sign in the alternate hypothesis test. Okay, a test is one-tailed when the alternate hypothesis states the direction either less than, which would be a left-tailed test, or greater than, which is a right-tailed test. In the case of saying not equal to, this means that your rejection area can either be greater than or less than whatever your critical values are. And so when you have that kind of situation, your alpha value actually needs to be divided into two. So if you have a rejection or an alpha value of 0.05, and you've done a two-tailed test, half of that rejection area needs to be in the lower tail and the other half goes in the upper tail. So let's look at an example. We have Jamestown Steel Company manufactures and assembles desks and other office equipment at several plants in New York State. At the Fredonia plant, the weekly production of the Model A 325 desk follows a normal distribution, a mean of 200, and a standard deviation of 16. So since we know the population standard deviation and they've told us that we have a normal distribution, we can go ahead and use the Z statistic that we're already familiar with. They have new production methods that were introduced, and the Vice President of Manufacturing wants to know if it's made a difference, right? So his question is my average the same? So because he is asking, is it the same? Our null hypothesis is that our population mean is equal to 200. And then our alternate hypothesis is that they are not equal. So when we're looking at equal, not equal, that means that we're doing a two-tailed test. And since this is a production situation, it is reasonable that we are using an alpha value of 0.01. So when a testing hypothesis about a population mean, if the population follows that normal distribution and the population standard deviation is known, you can calculate your Z statistic using that picture 2 formula that we talked about when we were looking at sampling distributions earlier. So step 4 is formulate the decision rule by first determining the critical values of Z. So since this is a two-tailed test, the level of significance was 0.01. We divide it into 2, so we're looking at 0.005. And so we have 0.005 placed in each tail, and that becomes the region of rejection. You can either find this value on the Z table, or you can use the student T distribution table. So to find the critical value using the student T distribution table, you're going to move along the top margin called level of significance for two-tailed tests, alpha, and then you're going to find the column for 0.01 and move to the last row labeled infinity. Because when we learn about t-test or t-distribution, as my number reaches infinity, my t-distribution becomes closer and closer to a normal distribution. And so when we look at this, we see the value in this cell is going to be 2.57. So this means that my critical values are going to be at positive 2.576, and then our other critical value is going to be at negative 2.576. So we're going to take a sample, compute our test statistic, and make a decision. So once again, since we're comparing sample means to population means, we're going to be doing x bar minus mu divided by population standard deviation over the square root of our sample size to get a z-value of 1.547. So if we go back and look at our picture, we see that 1.547 is in the unshaded region of our graph. So because of that, we're going to make the decision to fail to reject our null hypothesis. So since we have failed to reject our null hypothesis, we need to interpret that. And so since we did not reject the null hypothesis, we've also failed to show that the population mean has changed from 200 desks per week. So what that means is when you go in and talk to that vice president, you're going to tell the vice president that the sample information fails to indicate that the new production methods resulted in a change. So we also didn't quite disprove that the assembly rate is still 200 a week though either. So we failed to disprove it, which is not going to be the same thing as actually proving it to be true. Now, if this executive had asked, if there had been a change in the mean number of desks assembled and the vice president wanted to know if there was an increase, now we have a directionality in our hypothesis testing. Okay, so before we had a two-tailed test where we were wanting to know if it was the same or different, so equal, not equal. Now we're looking at a one-tailed test where we are looking at our status quo or less, which is 200 desks, and our alternate hypothesis would be greater than the 200 desks. So the critical values for the one-tailed test are going to be different from the two-tailed test at the same significance level, because in the two-tailed test we split the significance level in half and put half in the lower tail and the other half in the upper tail. So in a one-tailed test we can put all of that rejection region in one tail. So using that student t-distribution table, we can move along the top heading called level of significance alpha, select the column with alpha 0.01, and then move down to our last row, which is labeled infinity, to find that our z-value is 2.326. So we can have some errors in hypothesis testing, and this is something that when you do research, you have to state certain things, right? So after you've done the experiment, you need to talk about potential sources of error. And so there are two types that we typically look at. We look at type 1 and type 2. We're pretty original there. So with type 1 error, we select our alpha value, and that is looking at the risk that we're comfortable with accepting for our experiment of rejecting the null hypothesis when it's true. Okay, so if you are ever asked to evaluate the risk of your model, that's what you're looking at. You're looking at that alpha value. How big is that alpha value? The bigger the alpha value is, the bigger risk that you're willing to take that you're going to reject the null hypothesis when it's true. And then we calculate the beta value, which is used with type 2 error. And so it's not likely that type 2 error is going to occur, but it is possible for it to occur due to the process of random sampling from a population. And so here we look at the summary of the decisions a researcher can make and possible consequences. So here we have the null hypothesis. And if the null hypothesis is true and you do not reject, you've made a good decision. If the null hypothesis is false and you do reject it, once again, you've made a correct decision. But if the null hypothesis is true and you reject it, you've made a type 1 error. And to demonstrate that, we've got the situation of pregnancy. In the case of a pregnancy test, the status quo is that you are not pregnant. Therefore, the null hypothesis is that you are not pregnant. So, if a patient is truly not pregnant and you reject that null hypothesis, you have committed a type 1 error. Okay? Now, if the null hypothesis that you are not pregnant is not true and you fail to reject it, you make what we call a type 2 error. The formula on the left is going to be used to calculate the probability of making a type 2 error. And it finds the number of the standard deviations or standard errors, which is your z-value, between a critical value, which is designated as x bar sub c, and the sample mean, and that we can assume to be the true population mean, which is designated using the symbol mu. So let's look at a type 2 error example. We've got Western Wire Products purchases steel bars to make cotter pins. Past experience indicates that the mean tensile strength of all incoming shipments is 10,000 psi and that the standard deviation is 400 psi. So they're going to want to monitor the quality of the cotter pins. We're looking at samples of 100 pins randomly selected and tested for their strength. And so in this case, we're going to use an alpha of 0.05, which at that level, we're going to accept the shipment if the sample mean strength falls between our critical values of 9.22 psi and 10.078 psi. But if the sample mean does not fall between our critical values, we're going to conclude that the shipment does not meet our quality standard. So we have the sample mean of 9,900 psi is not within our specified range. So to calculate the probability of a type 2 error, we can assume that the sample mean is going to be the true mean that we see in graph B. So then we determine the probability of the sample mean falling between 9,900 and 9.922. Okay, and then we subtract the probability from 0.5 to arrive at the probability of making a type 2 error of being 0.2912. And so here we see that the probability of a type 2 error is 0.2912. We can also use that formula that we saw in the previous slide to do this calculation that was just discussed on your slide itself. And so that beta value is what we calculate to figure out the risk of making a type 2 error. We can also look at hypothesis testing with using our p-values. So remember, the p-value is the probability that the value of the test statistic is as extreme as the value computed when the null hypothesis is true. So a very small p-value, such as 0.001, is going to indicate that there's little likelihood that the null hypothesis is true. On the other hand, a p-value of 0.2033 means that the null hypothesis is not rejected and there is little likelihood that it is false. A p-value is the probability that the value of the test statistic is going to be useful, right? So if we look at our previous example about dust production, the z that we computed was 1.547, and we did not reject the null hypothesis. So now we're going to round the computed z values to 2 decimal places to get 1.55. And using the z table, we're going to find the probability of finding a z value of 1.55 or more by doing 0.500 minus 0.4394. So this calculation right here is using a z-table where they're looking at the area between the z value and the population mean, not from negative infinity. So anytime you see something where you have that random 0.5, that's what's going on there, is they're referring to a z-table that's only going to be cumulative away from the mean. But since this is going to be a two-tailed test, that area from the mean to the z-squared is going to be doubled, giving us a value of 0.121. So looking at this chart, we can easily compare that p-value with our level of significance. So when you look at your p-value and you look at your alpha value, then you make your determination, right? So here we have a p-value of 0.1212, which is greater than the 0.01 level of significance that was selected. And so in this case, the null hypothesis would not be rejected. So here we're looking at the average adult male is 5.8 feet. We have a random sample of 100 men that were found to have an average height of 5.77 feet, plus or minus 0.049 feet, using the 95% confidence interval. So knowing that information, is there evidence to suggest that the average height of the sample is going to be representative of the population? So here's a situation where we're using confidence intervals to test the hypothesis of whether or not my sample mean is representative of my population. So here we're looking at a two-tailed test because our null hypothesis is that the sample mean is representative of the population mean, meaning that they're equal or close enough to equal within the error range that we select. And our alternate hypothesis is that they're not representative or they're not equal. And so we look at the endpoints of our confidence interval. So 5.77 minus 0.049 gives us 5.72. 5.77 plus 0.049 gives us 5.82. And our population mean was 5.8. So 5.8 falls within this range. And so because of this, we're able to say that the sample mean is in fact representative of this population mean. And so in this case, we're going to fail to reject our null hypothesis. And once we've failed to reject our null hypothesis, we make the conclusion that our sample mean is representative of our population mean, and it's a good point estimate for us to use. So let's look at another hypothesis testing as confidence intervals example, but this time we're going to be looking at it in terms of proportions. So here we have the union representing the bottle blowers of America. They're looking at a proposal to merge with the Teamsters. So based on their bylaws, over 3/4 of membership must approve the merger. The estimate of the members who are in favor of the merger is 0.8 plus or minus 0.018. So basically they're estimating that 80% of the members plus or minus 1.8% is going to be in favor of the merger at the 95% confidence interval. So if we're looking at the 95% confidence interval, our alpha is going to be 5 or 0.05. And so our question is, can you conclude that the necessary proportion of BBA members are going to favor the merger at the 95% confidence interval, and why or why not? So here, the first thing we need to do is to come up with our hypotheses. So here we're looking at having over 3/4 of our membership in order for it to approve. And remember, your null hypothesis is your status quo. So that means that the null hypothesis for this needs to be less than or equal to 0.75. And so that our null hypothesis is that 75% or fewer of our members are going to favor the merger. And if our null hypothesis has failed to be rejected, our merger will not pass. Our alternate hypothesis then is going to be that our probability is greater than 0.75, or saying that more than 75% of our members are going to favor the merger, and the conclusion that would then be made is that the merger passes. So the endpoints of that confidence interval are going to be 0.782 up to 0.818. which is above the required value of 0.75. So when we're looking at confidence intervals for proportions, we calculated that the estimate of that proportion was 0.18 plus or minus 0.0018. I'm sorry, 0.80 plus or minus 0.0018. And so the formula result was that the lower endpoint was greater than 0.75. So because our lower endpoint was still bigger than the minimum value required for us to reject the null hypothesis, we are going to then state that we think that the merger is most likely going to pass.